showed us how to organize an SPA meeting in 2006, which was a huge success. And Jean continued to serve to guide those SPA conferences for multiple years. And I especially remember the wonderful meeting in Oaxaca. With Jean, I think you know it will go well. '60. We don't aspire to it, but it seems to sit lightly with Jean. So happy birthday. I'd like to talk about some recent work, which is joint with Vittorio Silvestri, who's in La Sapienza, Rome, Amanda Turner, who was at Lancaster. So it's in the area of continuum random growth. I suppose this is mainly interesting in the case when say d equals 2 or 3. That's all our work is in dimension 2. And one proposes some sort of physically reasonable mechanism for random growth, and the kind of the first question, the big question, is whether and suppose that the mechanism is somehow symmetrical with respect to rotation. Do the clusters which grow kind of preserve that symmetry, or do stochastic effects create instabilities and fractal effects? So you know, the big question in random growth is, one big question is whether you're in a stable regime or some kind of fractal or turbulent regime. And how can this work? Well, I mean, of course, it all depends on the mechanism by which your randomness comes into the growth process. But if parts of your cluster, which are kind of already kind of at extreme points of the cluster, if they are more likely to grow than other parts, then you can see how there can be an instability. On the other hand, sort of random effects may kind of average things out over time, and it could be for a different mechanism that that even if you started with something which was inhomogeneous, that it would sort of smooth down over time. So that's the question which I'm going to look at, and in fact, the positive results we have, I should say at the outset, are for the kind of easy side of this dichotomy, which is the stable regime. But there is some evidence that we've kind of reached the edge of the stable regime, so that we've at least for the kind of accessible models which we can do something with, that we've managed to show stability where stability is really there. Okay, so as I say, our work is all in 2 dimensions, in fact. Of course, 3 dimensions is very interesting too. But the point about the reason that 2 dimensions is easier to unlock is that there is the Loebner theory. Okay, so suppose I have some sort of random cluster, okay, in the plane, which should be compact and simply connected. Then I can, in fact, encode it by means of a conformal map. So I take some reference domain, which will always be the unit disk. Then I can find a conformal isomorphism of the external domains. I won't keep saying that, but when I draw this picture, I mean that phi maps the region outside the cluster, outside the unit disk, to the region outside the cluster. So maybe I should write it once. There's a conformal map, external domains. And this is provided to us by the Riemann mapping theorem. It's not unique at the moment, but it is unique if I insist that phi maps infinity to infinity and that there's no rotation at infinity. Obviously, we can't rotate the unit disk and it stays where it is, but if I'm going to make the second condition, then in fact, by the Riemann mapping theorem, phi exists and is unique. So this gives a nice encoding of objects which are hard to understand mathematically, namely compact sets, in terms of objects which may be easier to understand, namely functions, conformal maps. And in fact, phi has to have the following shape. That's a fact. This quantity here is called the conformal radius, or logarithmic capacity of the cluster K. So I mean, if the it is just the radius if K is a disk. Otherwise, it's some sort of measure of the size of K. It grows with K. If you have K contained in K primed, then C will be smaller than C primed. So, and I'm going to write, and this is a slight abuse because it's not a capacity in any conventional sense. I'm going to write C for the capacity of K. So one nice thing about this arrangement is that if I take the push forward of the uniform distribution on the unit circle by phi, then that gives me the harmonic measure from infinity on the boundary of K. Now, in general, that's a kind of, well, I mean, we know what it is. It's the hitting distribution of a Brownian motion wandering in from infinity, and you stop it when it hits K. So we understand it, but actually to do analysis with it when it's varying is a difficult thing. And so having kind of ready access to the harmonic measure through this map is something which helps to unlock the theory. Okay, now what happens when we start varying the clusters? And I'm only going to think of the case when the clusters grow. So there's the Loebner-Kufarev theory. So let's suppose that we have a kind of a process, a growing cluster. I'm not going to specify completely precisely what I mean by growing continuously, but there's no harm in just thinking that it means what it says, that somehow it doesn't have a jump as it grows. It just kind of gradually grows bigger. And then by a reparameterization, we may as well assume that the capacity of KT is equal to T. Then, in fact, the associated maps, the phis, satisfy an equation. Okay, so this here is some family of probability measures, vary with T. This here I'm using to denote just Z times the derivative of phi. So, I mean, the kind of the right way to think about what this is it's the radial derivative of phi. So how is this? I mean, how's this equation working? Well, I mean, if you imagine the clusters are, so what a picture like, you know, they've got a cluster and it's kind of growing a little bit here, growing a bit more. So for each of these, we have these maps phi t. So we can pull back the growth and sort of look at the growth at any instant happening on the unit circle. And what the equation is saying is that the kind of radial growth rate when pulled back to the unit circle is just given by this measure mu t. Okay, so I mean, this is a kind of amazing thing that any continuous growth of a cluster in 2 dimensions and reduces, in some sense, to the study of a family of probability measures on the unit circle. So you can pose the question, and this is a completely open question, you know, there are some putative objects which are out there that we'd love to get our hands on, namely scaling limits for models like DLA or the dielectric breakdown family of models. Supposing that there was a limit, then it would have to, it also, I mean, you know, a continuum limit. So this particle, you know, individual particles size is going to 0, so it grows continuously. It has to look like this. So what is the mu t? What is the process of probability measures associated with that continuum limit? I don't know that. There's potentially a very interesting family of measures out there which we don't understand at the moment. Okay, let's look at a few examples of the way this Levner-Kufarev equation works. So first of all, the most obvious case, I could just take a uniform distribution on the circle. Then if and let's suppose that I start with some sort of inhomogeneous set K0. Most of the talk I'm going to start with the disk as the initial cluster, but suppose I start with something no, which is not a disk. And then in fact what happens, and you can just solve the equation explicitly in this case, is that you can write down the solution in terms of the initial conformal map like that. So all we're doing, in fact, is to look at, so there is this map I0, which realizes the cluster as an image of the unit disk. And we're taking we're kind of growing this, we're taking a circle of growing radius around the unit disk, and then phi0 will map that to equipotential lines around the original cluster, and that's how the cluster grows under this dynamics. So this is clearly a case in the sort of smoothing regime. Okay, second example. We could take the mu-t to be a unit mass at some process wandering around on the unit circle. In the first instance, we could take it to be a Brownian motion of diffusivity kappa. Well, then the resulting family of clusters is the radial SLE kappa. So that's been extensively studied, and we know that's the scaling limit of some discrete models. Here's another example where the measure is a point mass. Suppose we take this process XIT, which behaves as follows. Suppose it jumps to an independently chosen point on the circle at times of a Poisson process at rate 1. Okay, then what's that going to? So I'm supposing that we have our process XIT, starts some place, stays there for a while, and then it randomizes to some other point on the circle, stays there from exponential time of parameter 1. What will the cluster look like? Well, in fact, what will happen then is that we start off by growing a little stick, and we grow another little stick, corresponding to the time when XIT is its second value, and it keeps growing like this. And the cluster will grow. And I'm thinking, in the end, I want to think about a case when there are very, very many particles, but they're very small. Stefan Roeder told me that, in fact, this model was once mentioned in the published literature and called stochastic Loevner evolution at some date prior to Schramm calling something else stochastic Loevner evolution. But the terminology is now, well, I guess we now call them Schramm Loevner evolutions. But this is something which kind of was proposed and then forgotten about some time before. Okay, here's another interesting case. I could take the driving probability measures to be feeding back information about the current cluster. So what I want to propose is to think about the case when we feed back like this. And I mean, in this case, if I substitute that family of probability measures into this Loevner-Kufarev equation, I'm going to call that the Loevner-Kufarev zeta equation. Okay, now this quantity here, the thing with the modulus without the power, has a physical interpretation as the density of arc length with respect to harmonic measure. So we have our cluster K. There are two natural, I mean, provided it's rectifiable boundary. There are two natural measures on the boundary, and one can play with both of them. There's the hitting distribution of Brownian motion, the harmonic measure from infinity, and there's the arc length measure on the boundary. Because of what I said about harmonic measure, it's just the image of the uniform distribution. This is kind of the harmonic measure. Then modulus of phi t primed d theta is just giving us the density of arc length with respect to harmonic measure. So let's think about when that's going to be big and small. If we're at a tip, an exposed point on the cluster boundary, that's going to attract a lot of harmonic measure for a small amount of arc length. So this density will be small. on the other hand, if we're right in a fjord, so if we're in a fjord, then if we're at a tip, small, which is really why there's a minus sign before the zeta. If zeta is large, then we're favoring the places where 5' modulus is small, so we're favoring the tips. And if zeta is small or negative, then we're favoring the fjords, and we'll fill in the fjords, the preference of the tips. So if zeta increases, we expect the stability to decrease. If I were to take zeta equal to 0, I'd be back with the this case 1, when we can solve the equation explicitly. If I took zeta equal to 2, then the equation is quite well studied because it's associated with a Healy-Shaw flow. And it's known that the nonlinear equation is ill-posed in this case. This is somehow related to DLA in a way which is not completely understood. So there are reasons to expect that this equation, the nonlinear equation, where you feed back the current cluster into the Levner-Kufarev equation as in 4, you expect this behaves stably. For zeta less than or equal to 1, and unstably for zeta greater than 1. But this is very open. And although this looks like a fairly natural equation, I mean, apart from the Healy-Shaw case and the trivial case, it's not really been studied. In particular, although I think I'm guessing that there's a nice theory for zeta less than or equal to 1, well posed and so on. Don't know that. But you can spot some solutions. There are always disk solutions. Okay, so they have this form. So phi t of z is just e to the tau t of z, where tau t is the log of 1 plus zeta t over zeta. So it's just a multiple, a positive scalar multiple, growing scalar multiple of z. So this corresponds to the clusters just being a growing family of disks of radius e to the tau t. You substitute that into the equation, you can see that it works, but we have no theory that says well, okay. So for analytic initial data, I should mention one of here's a current PhD student. So Oliver adapted some work from the Healy-Shaw case to show that you have short time existence of solutions, but I mean, it only appears to be short time existence, and for zeta less than or equal to 1, there should be long time existence and uniqueness. Okay. Right, so I should tell you what the model is for our random growth, which I've not done yet. So this is the so-called aggregate Levner evolution model. And it has the following data. So I need a family of particles of varying sizes. So just to fix ideas, we could attach them all at the point 1 on the unit disk and just consider a nested family of little disks tangent to the unit disk. So I want my particle family to be nested. Now, each of the and the C is there because if I look at the cluster formed by the union, I mean, generally the PCs will be very small, so it's not a very good picture. It looks more like that. So the cluster formed of the particle and the unit disk. This is the unit disk U. That should be C. And I'm going to be considering limits where C goes to 0. So it's going to be a little disk attached to the unit disk. And so, you know, this will have a map F. Unit disk should be the same size in the two. So let FC be the kind of Riemann map, which adds the little particle to the unit disk, tangent to the disk at point 1. Okay, but I mean, it doesn't have to be disks. These could be slits. They could be. I mean, the results that we have some kind of. They don't really depend on the shape of the particles, but it is convenient to insist that they're nested. Just for some orientation, the radius of PC will then be of the order of the square root of C. Okay, so in the model, there are then 3 further parameters. There's, first of all, a regularization parameter. And so this is a way of softening the model, making it easier to handle. And so instead of feeding back, at least on the stochastic side, instead of feeding back information about the current cluster through exactly the, where is it? Yeah, through the density of arc length with respect to harmonic measure on the cluster boundary. What's going to happen instead is that, you know, if I have my current cluster like this, I'll move out a little bit from the unit circle, which gives me a slightly smoother particle cluster, and use the density of arc length with respect to harmonic measure there to feed back in determining the dynamics of the cluster. Okay, so, and there are also 2 further parameters, alpha and eta, which take real values, and we can vary them to get an interesting class of models. Okay, so what is the model? It's a continuous time Markov chain. It takes values in the, I mean, if I write S, the set of the possible phi's, that's going to be the state space. So what's the rule for jumping? It's a finite rate. Markov chain. If it's in state phi, say, it jumps to phi composed with f C of theta and phi theta, and I'll explain that in a moment, at rate lambda of theta and phi, which I also have to define. So some quantities there have not been defined yet. So first of all, fc theta of z is just e to the I theta fc of e to the minus I theta of z, and this just rotates. To attach the particle not at 1, but at theta. It's a sort of e to the I theta. But then I'm got to explain what c and lambda are. So c of theta and phi is going to be the capacity of the particle that we add in the jump. Will be c, sort of the parameter c, multiplied by phi primed at e to the sigma plus I theta the minus alpha. And lambda of theta and phi will be c to the minus 1 phi primed e to the sigma plus I theta minus eta. So this is a little bit reminiscent of the Levner-Kufarev zeta equation. I'm going to consider the limit c goes to 0, and also at the same time the sigma is going to go to 0. So, I mean, what does this jump do? So the jump adds to the cluster the following set: phi of e to the I theta, p c of theta and phi. So it adds to the current cluster what we obtain by taking from our family of particles the particle of capacity c of theta and phi, and then moving that round to the position e to the I theta on the unit circle, and then pushing it out to the cluster using the current conformal map. Okay, and throughout in considering all these models, I'm going to be considering starting the initial state to be just Z, which means we start our initial cluster is the unit disk. Okay, so this is a class of models. Let's look at some special cases to get some orientation on what's going on. Maybe it'd be helpful to just say that suppose we've taken n jumps by time t, then in fact we'll have n particles, and the conformal map associated to the state of the system at time t will be of the following form. It'll be just a composition of maps f, each of which corresponds to addition of one particle like this. Okay, so here are some cases of this dynamics. So if I take alpha and eta to be 0, it's the easiest case, then this makes the fn's independent. So it's just a composition of independent conformal maps, each of which is a small perturbation of the identity. This is as close as the talk gets to Levy processes. So I'm sorry, Jean, I was not able to to find something which is more directly of interest. And anyway, so this is the most straightforward case to analyze. It's the so-called HL0 model. And there's a bit of literature on this. So the whole family was proposed, well, the whole family I mentioned in a moment was proposed by Hastings and Levitov, there was some earlier work by Roeder and Zinsmeister in understanding the behavior of HL0. And I had a look at it with Amanda, and more recently, Vittoria also looked at the fluctuations of this model. So, I mean, obviously the independence of these FNs makes it more approachable than some of the other variants. Okay, if alpha is -2, then this has the effect of, well, and let's specify the other parameters as well. We'll just take the eta to be 0 and no regularization. So this was proposed by Hastings and Levitov. As a surrogate for DLA. I mean, DLA is classically a lattice-based model. The lattice structure has some problems there because it seems to remain there in the scaling limits. So one's looking for off-lattice ways of conceiving DLA, they get even harder. But so this was looked at by Hastings and Levitov as a way to use complex analysis to produce something like DLA. And they, so this would be HL2. And in fact, you know, there's also HL alpha when you don't put it exactly equal to 2. This is one of the models considered by Hastings and Levitov, and they investigated this numerically, and their conclusion was this: that if alpha was less than or equal to 1, then you had a sort of smoothing evolution, or just at least not getting worse evolution. Alpha equals 1 is a kind of boundary case, obviously, and alpha is bigger than 1. They saw stochastic effects on large scales, even with very small particles. So this is a conjectured phase transition, and at some level, what we've done is we've shown this is the case, but I mean, I shouldn't claim too much. Only up to the so we've made our lives easier by the introduction of the regularization, and I have more to say about what sigma can do in the limits we consider. But our results reflect this phase transition. So other prior work. So Alan Solar, along with Amanda Turner and Frederick Wickland, I got the wrong order. No, it didn't. Have studied these models, and they showed for a particular model that indeed you had unstable behavior when alpha was bigger than 1, any alpha bigger than 1. They also showed that if sigma was too big, in another paper, well, I mean, it's still going to 0, but more slowly. That in fact, the phase transition disappears. So this is a bit of a mystery because it was believed that you had this phase transition to alpha equals 1. No phase transition. And what we've shown is if that sigma goes to 0 a bit faster, then indeed you do see this phase transition. Okay. Should try and motivate a little bit this alpha equals 2, alpha equals -2 choice. In one sentence, by taking alpha equal to -2, one contrives to get particles added to the cluster which are all of roughly equal size and don't in some curious way depend on the position that they're attached. The size doesn't depend on the position that they're attached to the current cluster. So to justify that, If I took phi, no, this is not the case. So this is a slightly misleading argument. If phi was smooth and C was small and alpha was -2, then we could do a kind of Taylor expansion of the conformal map. So if I took Z in the cluster which I was adding, then phi would be approximately linear because it's smooth, so on small scales it's linear and looks like this. So that the scaling up factor for the so you would you wouldn't see very great distortion of the cluster. You would just see a scaling of it and rotation of it by this derivative. And the choice of C of theta and phi is to kind of remove the scaling aspect of that. So the radius, therefore, of the particle that you add, which I just remarked was phi of e to the I theta pc, would then be approximately, I said that the scale of the particle was the square root of the capacity. So that would be the square root of C phi primed e to the I theta to the -2. Right, that's the -2 from the alpha. But then from this Taylor expansion, you also have the modulus of phi primed of e to the I theta as a scale factor, which then enters because we're looking at the image of e to the I theta pc under phi. Okay, and so that by taking alpha to the -2, these two things cancel. That's why alpha equals -2 is kind of a nice choice. I would say that the regularization parameter weakens the particle interactions. So it's a way of making the math easier. Okay, so here are our results. First of all, there's a disk theorem. I'm going to state them a little imprecisely, because I think it makes it easier to understand. They're stated precisely in the posting on archive. So I'm going to be looking at the limit as C goes to 0 and sigma goes to 0. And I mean, a key thing that we find is that the bulk scaling limit of this growth model only depends on the sum of the two parameters, alpha and eta. So, I mean, you can see why this might be the case, because this is kind of law of large numbers effect. We're adding particles whose size is modulated by alpha at a rate which is modulated by eta. So sort of those two effects should kind of work together to produce the kind of continuum growth rate. Okay, so if zeta is less than 1 and sigma is not too small, and too small in this case means some power of C just a little bit less than half, then ALE alpha eta grows disk radius dot T, which is given by 1 plus C to T. So, I mean, it looks like the disk solution of the Loebner-Kufarev zeta equation. You might worry what happens when zeta is negative, because this hits 0. And so if zeta is negative, we're only making this claim. So the disk, in fact, kind of goes to infinity as t increases to the modulus of zeta, the -1. Yes. And there was the limit is only claimed for t less than that limit value. Something pretty much the same happens for the critical case. And there we require a bit more regularization, c to the 5th minus epsilon. But the same sort of story, it's a disk of radius 1 plus t. Okay, so yeah, I mean, it's kind of worth remarking on. So this includes within the sort of parameters which we can work with, the case when alpha is -2 and eta is equal to 1, and that's a kind of Eden-like model. The Eden model is a lattice model, but it's a continuum version of it's like this, that we've kind of fixed the particle sizes to be roughly the same, at least if you believe this story about motivation there. And by taking eta equal to 1, we've changed eta equals 0 gives you attachment distribution, which is harmonic measure. Eta equal to 1 then shifts that to be the arc length measure. So it includes that case, but I guess reassuringly, it doesn't include the case when alpha is -2 and eta equals 0, which would correspond to DLA. DLAs in the simulations is very fractal. So if we were getting a disk in that case, we really would be up the wrong tree, I think. Okay, so that's the sort of bulk scaling limit of the model. And we can also show a fluctuation theorem. And this is possibly not as expected, but I emphasize this point. Taking smaller values of sigma than we currently allow could produce different fluctuation behavior. For the range which we can consider, we get the following Gaussian limit. Okay, so I'm going to write TT for the capacity of the cluster at time t, which is just given by the logarithm of it primed at infinity. It's a positive quantity. And then what we can show is that if zeta is less than 1, and a slightly kind of stricter condition on the regularization than for the bulk scaling limit, so sigma is greater than or equal to 1/4 minus epsilon, or zeta is 1 and sigma is greater than or equal to, gets a little bit worse there again, 1/6 minus epsilon, then, okay, so I'm going to normalize the conformal map in 2 ways. First of all, I'm going to adjust it so that it has derivative 1 at infinity. And then I'm going to subtract the limit object, scaled in a similar way, subtract z, but divide that by the square root of c, and I look at the whole process for, I guess, t greater than or equal to 0, mod z bigger than 1. This converges weakly in a suitable sense in some space of conformal maps to a Gaussian limit process, which I will describe. This is as c goes to 0, sigma goes to 0 with these constraints. And in fact, I mean, the one point to emphasize is that although one loses everything about alpha and eta in the Bolt scaling limit and only sees their sum, the two models, the models can be distinguished by looking at their fluctuations. So here is the specification of the Gaussian limit. You can sort of code it up as a kind of stochastic differential equation in conformal maps. So tau t, if you remember, is this. It's the radius of the disk solution at time t. So e to the minus eta t over 2 dbt of z minus a. Let's say what at is in a minute. Gamma t of z e to the minus eta tau t dt. So a is an operator on holomorphic functions, which have Laurent series, and it can be written like this, where d is that radial derivative I defined before. It's a multiplier operator, which is that's one of the key techniques in proving the theorem, that we use some multiplier operator estimates. It acts as kind of 1 plus 1 minus zeta k on z to the minus k. Okay. That's described A, but what is B? This is a kind of Brownian motion in holomorphic functions outside the unit disk. And the BTKs are independent over K, complex Brownian motions. Okay, so that's a complete description of the limit object. In fact, this whole equation, this is slightly dressed up to look more impressive than it really is. The equation diagonalizes. You can split it into independent equations over the different Fourier modes, different Ks in the excuse me, in the Laurent expansion. And each of the modes, the equation is doing it independent, almost an Uhlenbeck process. The restoring force in the kth Fourier mode is this multiplier. So you see that when k is large, provided zeta is less than 1, then you're kind of damping down the higher Fourier modes quite quickly. You see this beginning instability when, well, your edge of stability when zeta is equal to 1, because you no longer have kind of preferential damping for the higher modes. And if you kind of formally chose to look at zeta being bigger than 1, which we have no theorems about, then what's happening is that the fluctuations in the higher Fourier modes are growing exponentially faster rather than being damped. So it's looking very much as if the whole thing is unstable in that case. Okay, I should stop there and very happy to answer questions.
Thank you very much for the interesting talk. And are there questions in the audience?
Hi, James. So the central limit theorem that you presented is about the global fluctuations. So I was wondering whether it would be also possible to have a more local view at it, in particular in relation with, let's say, for instance, if we are optimistic, KPZ,
Sure, that's I can't say anything. This is certainly a question of interest, but there's nothing substantial to report. It appears that one should look for one needs to understand the case when the regularization parameter sigma is allowed to go to 0 faster. And as you say, one should be looking at a more local scaling limit. But you know, since the Eden model is conjectured to have KPZ fluctuations considered in the right scale, this is something which, in some sense, one would expect for the zeta equals 1 case also.
Other questions?
Okay. Yes, I have a question. I'm Nathanael Enriquez. I don't know if you can see me, but
yeah, you're on the screen now.
Yes, it was a wonderful talk. Thank you very much. I was just, I have a naive question about the Loevner-Kufarev evolution. And it seems that zeta equal 1 seems to be a frontier, but I don't understand why, because it seems to me that the larger the zeta, the smoother the evolution.
Okay, so I think I can answer your question. So, where are we? Yeah, so there was this comment here that the
yes,
when the I mean, it's slightly upside down, right? The mod phi primed is large in the fjords, right, deep inside the cluster, which you can't get to very much by Brownian motion, and it's small. I seem to have lost that. It's small on the tips of the cluster. So the effects of the of choosing this.
You add the less mass when on the fjords when zeta is large, you mean?
Yes, that's the way it goes.
Okay. So it was exactly the reverse.
Okay.
Effect.
Yeah.
Okay.
And I mean, I guess maybe it's slightly deceiving. I put a minus.
Yeah. Yes.
But let me say why the one should be the frontier. So in some sense, you've got already one derivative outside here. And when you take zeta equals 1, you're balancing it exactly with the derivative on the mu.
Mm-hmm.
And that's why it's not kind of zeta equals 0, which is critical, but zeta equals 1. Sorry, you were going to ask another question.
Yes, and so the internal GLA evolution should correspond to which to zeta equal 0 or to zeta?
So this was a link which seemed to appear when Vittoria looked at the fluctuations for the HL0 model. In the
so zeta is equal to 2 is is not circular at
no, well, so it has a disk solution, but it's unstable.
Okay.
In any kind of physical realization of the Healy-Shaw flow, you don't see the disk. You see a kind of fractal behavior.
Okay. Okay.
So sorry, you also asked a question about internal DLA.
Yes.
so there it kind of, instead of favoring the tips, it favors the fjords.
Yes.
Right. And it actually, it seems to be quite close to the behavior of HL0 in terms of fluctuations.
So the data is negative, maybe, or just in that.
I don't want to give you a definite answer on that, but what Vittorio Silvestri found for the HL0 model was that the Gaussian fluctuations were very, very close to the fluctuations found by Sheffield and some other people who looked at the fluctuations of internal DLA.
But it was a logarithmic.
So, yeah, kind of a logarithmically correlated Gaussian field.
Okay. Yes, yes. Thank you very much.
Okay. Then now you want to ask your question?
Hey, hello.
Hi.
James, I want to ask you a question about your, maybe a naive question about your terminology. I was wondering what you mean in your main theorem, grow as a disk, the terminology grow as a disk, what the meaning of that. Also, I have a second question about the phase transition you mentioned. You said that there is a phase transition between some kind of smooth behavior and some fractal behavior. And I was just wondering how you can classify certain KT as fractal growing, or some KT is smooth growing. I'm just wondering this. Thank you very much.
Okay, yeah. So I mean, the imprecision is mine. So the disk theorem is in fact a reasonably tight estimate, which shows that the associated conformal map, the phi t, is close to the corresponding disk solution of the Loudner-Kufarev equation. This will translate into some kind of estimates on the cluster being contained within a disk of radius slightly bigger than the disk solution. In fact, there will be little gaps inside the cluster in general. So it has this kind of nice internal structure, which I looked into in another occasion, where you can sort of track the ancestry of particles inside as coalescing Brownian motions. So it's not a disk in that sense, but if you kind of look at it with your eyes slightly unfocused, it is exactly a disk. Sorry, you asked another question.
About the phase transition between
yes.
and
So I mean, I don't have any positive results about the fractal case, but something which I was going to do and didn't, and might be of interest, is to just show you some pictures. I started off with one picture, which was this one. So that's an illustration, in fact, of the case when the HL alpha model, when alpha is 1 and where sigma is the square root of c. So it's just off the range that we can handle, and it appears to be a rough disk. So let me show you a couple more pictures. If I take HL0 again, it's like a disk. If I move the alpha up a little bit to 1.5, then one sees that there are sort of stochastic structures on macroscopic scale growing. So there may be two ways one could think of this as being fractal. One is it has a sort of intricate internal structure, and that's not really the one which I'm talking about. But if you let this develop a lot longer, then you would see the inhomogeneities in this grow and grow. And I mean, I'll give you a slightly more extreme case to look at. This is a picture of the case when zeta is equal to 2, so this should look like DLA. It doesn't look like the classical simulations of DLA, I think because of the regularization which is taking place, the fact that there is still some regularization, but you can see that it's starting to look kind of a much more interesting picture than the disk ones that we can prove theorems about.
Yeah, okay, thanks. That's much clearer now. Thank you.
Okay, so it looks like there is another question. Do we have time? Or very quick.
Thank you. Okay, so quick question. Both in your disk theorem and in your fluctuation theorem, you had conditions on the speed at which the regularization parameter converges to 0. Is it simply a technical condition, or do you expect really different behaviors depending on the speed of convergence to 0?
I expect to see different fluctuation behavior. But I don't know, maybe I should be careful what I say. I don't think it's simply a technical restriction. I think there are, so the restriction to kind of 1/2 minus epsilon seems to me likely to be kind of actually there. The various other powers of C which appeared are more questionable. But it's a very good question, and I think it's work in progress to really try to answer it.
Okay, we can thank the speaker again. Okay.